Hey guys, welcome back to chapter 16. What we're going to do in this video is we are going to add a salt to solution and we are going to determine how it changes the pH. So we're going to quantify this. We're actually going to use some numbers today. All right, so just as a review quickly, so if we add a salt to solution, the first step is going to be determine if that salt is going to have an effect and if the effect is going to be a basic or an acidic effect. So remember, we break the salt apart into its cations and anions, remove any conjugate of strong acids and bases, remove any metals with a +1 charge, and then determine how the remaining ions affect the pH. Okay. So here we see sodium fluoride. Oops, it should be sodium. We break it apart into its ions, so sodium and fluorine. Sodium is a metal with a +1 charge, so that's not going to affect the pH. That's going to be neutral. Fluorine is a conjugate of a weak acid. So again, if we use our A-B method, fluorine is going to have a basic effect. Okay, so fluorine is going to act as a base when we put it into solution. So up until this point, that's review. Now, how do we take that information and apply it to a pH problem? So the first step at this point is going to be to write a balanced equation for that basic anion or acidic cation. So in this case, we're dealing with fluorine. So we are going to write exactly how fluorine is going to affect the pH. So fluorine is going to react with water. So water will always be the reactant that we put our ion with. So fluorine will react with water. We already decided that fluorine is going to have a basic effect. So fluorine is going to act as a base. Bases are proton acceptors. So his conjugate will be the addition of a proton. If he is acting as the base, that means water is going to act as the acid. So water is going to be a proton donor. So when water water donates a proton, it's going to be left with just that OH minus. Okay. So that's the first step to determining how the pH is affected. Next, we're going to write a Ka or Kb. Get rid of this. Next, we're going to write a Ka or a Kb for this equilibrium equation. So again, it's going to be important to know if we're dealing with an acid or a base. In this case, we decided that this is a base. It's going to have a basic effect. So we are going to write the Kb for this equation. Okay. Kb, remember, is just products over reactants. So concentration of the products over the concentration of the reactants. And that's our Kb for this. And at this point, we would solve for an equilibrium problem. We'd solve the equilibrium problem, and we'd either solve for OH or H, depending on our vantage point. In this case, we're doing Kb, so we're going to solve for OH, and then we would take OH to POH to pH. Okay, so that's how we would solve for this problem. So the best way to do this is just to dive in. So we're going to dive into a problem together and work through it nice and slow. What is the pH of a 0.1 molar NaCHO2 solution? Take you just a minute to kind of assimilate to this problem. We'll start working it together. First step here is to recognize that this isn't a classic acid or a classic base. So you need to recognize it first and foremost as a salt. So that's one of the first steps, is recognizing that as a salt. Once you recognize it as a salt, we need to determine what kind of salt is it? What kind of effect is it going to have? So break this apart into its cations and anions. Get rid of any metals that have a +1 charge. So those are just spectator ions. So sodium is a spectator ion. It's a +1 metal. The anion, so is this one of our big five? Nope. This is the anion of a weak acid. So if we use our AB model, this is going to act as a base. So ultimately, the pH should go down. Nope, just kidding. Should go up. Become more basic. Okay. All right. The next step is to write an equation for how this base is going to perform, so how it's going to act. So we've got our HCO2. It's acting as a base. It is going to interact with water. If it is acting as a base, that is a proton acceptor. So on the other side, it's going to be HCHO2. And if he's acting as a base, that must mean water is acting as the acid. So acids are proton donors. So this is going to be OH minus. Okay. All right. So we've got our salt. We determined it's going to have a basic effect. We wrote down the equation. Now we're going to write the KB. Okay. So again, base. We're going to write the KB value, and that is just products over reactants. So we've got HCHO2, OH minus, and then CHO2 minus. Okay. So if I want to know what is the pH, I eventually need to solve for the concentration of hydroxide. Once I solve for the concentration of hydroxide, then I can move forward and get to pH from there. Okay. So this is going to need an ice table. So let me write that equation down again underneath this. Okay. So we're going to need our ice table in order to solve this. Initial, so when it says, what is the pH of a 0.1 molar solution? So we're going to assume that when this goes into solution, when we dissolve this in water, that it's going to completely dissociate or completely break apart into its ions. So if we put in a 0.1 molar solution of this, that means the concentration of the CHO2 is still going to be 0.1 molar. So that is the initial concentration. No mention of the other two. We're going to assume that they are 0. So now we can fill this in. So the change, the only way for these guys to go up is to change by a positive X. This one's going to change by negative X. Whoops. So we're going to have 0.1 minus X, X, and X. So then we turn to our KB equation, and you see that I've given you the value for KB. So 5.6 times 10 to the negative 11th Concentration of our products, so that's X and X. Concentration of our reactants, 1 minus X. And as always, I'm going to assume here that X is small and solve from there. So if I get rid of that X, we've got 5.6 times 10 to the negative 11 equals X squared over 0.1. To get X by itself, we're going to multiply by 0.1. Those cancel. And then, let me get my calculator here. We're going to take 5.6 times 10 to the negative 11 times 0.1 equals, so we'll have 5.6 times 10 to the negative 12 equals X squared. Then we'll take the square root of that. So X equals 2 just in the sake of space, we'll call it 4 times 10 to the negative 6. Okay. So I'm just going to validate this really quickly, make sure it was valid. So we would take 2.4 times 10 to the negative 6 divided by 0.1 times 100 to make it a percentage. So divided by 0.1 times 100. And this is 0.002%. So very much that was valid, well under that 5%. All right, great. We solved for X, but what does that even mean? So X is the equilibrium concentration of hydroxide, and ultimately we're trying to get to pH, okay? So if X equals 2.4 times 10 to the negative 5th, our hydroxide concentration at equilibrium is 2.4 times 10 to the negative 5th. To get the pOH, I'm going to take the negative log of that. So pOH is negative log 2.4 times 10 to the negative 5th. We get 4.62. And then pH is 14 minus pOH. So pH equals 9.38. All right, so does this make sense? Yes, it should make sense because the ion that's having an effect on the solution is having a negative effect, an basic effect, and because it's having a basic effect, we see that the pH is a basic pH. I hope you guys found this helpful.